Hello everyone, today we're going to be talking about first order RC circuits. More specifically, we're going to be talking about the general solution to find for the voltage across a capacitor for some time between 0 and infinity for a first order RC switch circuit. And that function is shown below. The voltage of the capacitor for that time between 0 and infinity will be equal to the voltage of the capacitor as time approaches infinity plus, in square brackets, the voltage of the capacitor at time equal to 0 minus, which means immediately prior to time equal to 0, minus the voltage of the capacitor as time approaches infinity. All of that was in square bracket, e to the negative t over tau c. What is tau c and what are these voltage capacitors that I'm talking about? We're going to go step by step and explain what they are and how you solve for them in a given circuit, and we'll do two examples of that. Okay, so first, Vc of t approaching infinity, that's infinity, is Vc at time equal to infinity in DC steady state mode. Vc of t equal to 0 minus is Vc at t equal to 0 minus in DC steady state mode. Tau c is equal to the time constant of the first order RC transient analysis. But more specifically, tau c is equal to R Thevenin times C. More specifically, R Thevenin is going to be equal to what? It will be equal to the equivalent resistance between the nodes created after it'd be the equivalent resistance between the nodes created after removing the capacitor from circuit and zero out all sources. So it's very similar to R Thevenin, as shown in Thevenin equivalent circuits. Tau c is R Thevenin times C. R Thevenin is the equivalent resistance between the nodes created after removing the capacitor from circuit and zeroing out all your sources. What's a great way to familiarize and get a hold of this general formula, which I'm not going to derive in this video? You can learn about it on YouTube on someone else's video. It requires differential equations. I'm not doing it. But how can we get a hold of these 1, 2, 3 values that are necessary in order to get down to this function? 4 if you consider R Thevenin. Let's do a practice problem. Okay. Let me get the practice problem in front of me. Okay. Let's call this example number 3-10-2. Okay. Let's assume I have the following circuit. Okay, so this is, let's call this R2, let's call this R1, let's call this VS, let's call this VS of T. VS of T, let's call this C, plus, minus, let's call this VC of T, Okay? And let's say that the switch closes at time equal to 0. Okay? So let's assume we are given the following values. Vs of t is equal to 4 volts. Does not change with time. R1 is equal to 10 ohms. Assume R2 is equal to 10 ohms as well. And assume C is equal to 1 microfarad. Okay. And assume that the capacitor is fully discharged prior to t equal to 0. So assume capacitor is fully discharged prior to t equal to 0. What does that mean mathematically? It means Vc of t equal to 0 minus is equal to 0 volts. We were given that. That's what it means. I hope they taught you how to understand the English translation to the mathematics in your class. Okay, now, question number 1. What is the steady state voltage? What is the steady state voltage across capacitor after the switch has been closed for a long time? After switch has been closed for long time. Okay. What is that asking for? At t equal to 0, the switch closes. So if we're talking about the the switch has been closed for a long time, then that means we are solving for what? Vc of t approaching infinity. Why? Because the problem statement indicates that the switch closes at time equals to 0. If the switch closes at time equal to 0, and the switch has been closed for a very long time, then that means your time has been approaching infinity. The switch has been closed for a long time. How do we do that? And I just want to go back real quick to my notes from earlier. Vc of t approaching infinity is the voltage of the capacitor at t equal to infinity in DC steady state mode. So we have to redraw this circuit at t equal to infinity or t approaching infinity, and we have to assume DC steady state mode. So let's do that. Redraw circuit at t approaching infinity in DC steady state. We have the voltage source, we have the resistor, this resistor, we have an open circuit, plus, minus, Vc of t approaching infinity. This is R2, this is R1, this is Vs of t. And this is t approaching infinity. T approaching infinity. Okay? So if you look at this circuit, you should notice Vc of t approaching infinity is equal to the voltage of R2 as time approaches infinity. And what? We can use voltage divider law to solve for voltage across R2 for t approaching infinity. So let's do that. VR2 as t approaching infinity is equal to the voltage across the capacitor as t approaches infinity, which is equal to the voltage of the supply as t approaches infinity, divided by R1 plus R2 times R2. What is the voltage of the supply as time approaches infinity? Go back to the problem statement. It was given that Vs of t is 4 volts indefinitely. So it's 4 volts divided by 10 ohms plus 10 ohms times 10 ohms. And you should get 2 volts is equal to the voltage of the capacitor as time approaches infinity. Again, we were given a circuit as shown here. We assume time is approaching infinity because the switch has been closed for a very long time. We assume in DC steady state, so we redrew our circuit as shown here. There's an open circuit at the capacitor now, and it's in parallel to R2. That is why VC of t approaching infinity is equal to VR2. So I should say C, or open circuit voltage. Open circuit VC of t approaching infinity is parallel to R2. That's what I meant to say. And we used VDL to find the voltage across R2. We plugged and chugged, and we got a number, 2 volts. Cool. Moving on. Question number 2. What is the time constant in microseconds of circuit? Okay. Before we answer that, I need to modify something from my notes. Sorry, I just realized I made a mistake. R Thevenin is the equivalent resistance between the nodes created after removing the capacitor from circuit and zeroing out all sources for t approaching infinity. Okay, again, that's for t approaching infinity. So let's go back here. So we're trying to find the time constant in microseconds. So time constant in microseconds of the circuit. How do we do that? We need to redraw circuit for time approaching infinity. What else do we need to do? We need to remove the capacitor. We need to zero out all sources. Then we need to find R Thevenin, which is equal to R equivalent between nodes created by removing the capacitor. That's not correct. Capacitor. And again, this is finding R Thevenin, R equivalent for the entire circuit between nodes created by removing the capacitor. Yeah, so, and let's do that. Okay. So we redraw the circuit, we have the battery, we have the resistor, we have the closed latch or the closed switch, we have the other resistor, and then we would have had the capacitor right here, correct? Okay, this would have been the circuit, but we have to remove the capacitor. So this is called as A plus, it's called as B minus. We need to zero out our sources. So I'm going to remove the battery, replace it with a what? Wire. And now I have to find R Thevenin. So by simplification, you should see that R1 is parallel to R2. And this becomes just one resistor. So, and this resistor is called R Thevenin, which is equal to R1 parallel R2, which is R1 times R2 divided by R1 plus R2. That's our R Thevenin, but we're looking for tau. So this was the second step. Third step is tau is equal to R Thevenin times C, which is equal to what? R1 times R2 divided by R1 plus R2 times C. That is tau. And if you get your answer in microseconds, we usually call it tau of capacitance or time constant of capacitance. So I'm going to put the subscript. I should have put it up in the very beginning as well. No, I did. Okay. So tau C is what? 5 microseconds. Ten ohms plus 10 ohms times 1 microfarad. All right, so let's recap. What is the time constant of the circuit? Well, we look at the circuit and we're going to realize that we need to look for the circuit or redraw the circuit for time approaching infinity. So let's do that. By redrawing the circuit for time approaching infinity and removing the capacitor and zeroing out all our sources, this is what we are left with. See, because the capacitor would have been here, but it's not anymore, right? And the voltage source became a wire. And so, yeah, so if you simplify the circuit, you get R Thevenin is equal to R1 parallel R2, and tau C is R Thevenin times C. Then the last question is, what is VOC at t equal to 2 microseconds? Okay. We're looking for voltage of the capacitor at t equal to 2 microseconds in units of volts. How do we do that? Vc of t equal to 2 microseconds is equal to the equation, which is Vc of t approaching infinity plus, in brackets, Vc of t equal to 0 minus Vc of t approaching infinity, close bracket, e to the negative t over tau c, where Vc of t approaching infinity was equal to 2 volts, Vc of t equal to 0 minus was equal to 0 volts as provided by the problem statement, and tau c was equal to 5 microseconds. By plugging this all into the equation, Vc of t equal to 2 microseconds is equal to, one second, it's between 0.6 and 0.7. I mentioned this because it really depends how many significant figures you're going to be keeping and how you do your unit analysis. So any answer between 0.6 and 0.7 is acceptable. Okay, that's the first practice problem. That all came from what? This circuit. Now let's do another practice problem. 1 second. Okay. Let's call this example number 3-10-3. Okay. So we have a capacitor with a resistor, and a current source. This is, call this IS1 of T, call this R1, it's on my stylus, R1, 3, 2, this is the capacitor, plus, minus, VC of T. Now, assume the following is given. C is equal to 10 microfarads. R1 is equal to 1 kilo ohm. R2 is equal to 3 kilo ohms. Kilo means 1,000, so 3,000, 1,000. And R3 is equal to 4 kilo ohms. And IS of T is indefinitely equal to 1 milliamp. Okay. The switch, where's the switch? Ah. The switch closes at time equal to 0. Okay. So again, the drawing is showing that the switch closes at time equal to 0. Okay. First question. What is the voltage of the capacitor just prior, again, just prior to time equal to 0? So what is another way to ask this question? Okay, another way to ask this is equal to, assuming the switch has been open for a long time, comma, what is VC of T equal to 0 minus? That's what the question is asking. What is the voltage of the cap just prior to T equal to 0? That's the same thing as assuming the switch has been open for a long time. What is the voltage of the capacitor right before T equal to 0 when the switch closes? So, how do we do this problem? Steps. 1, we're solving for the voltage of the capacitor at time equal to 0 minus in units of volts. How do we do this? Redraw circuit for T equal to 0 minus and in DC steady state. So let's do that. DC steady state means what? Our capacitor becomes an open circuit, and we're at T equal to 0 minus, so the switch is open. So let's redraw it. So we have the switch open, so I'm going to put that the switch is open. Then we have another open circuit. Notice in our drawing, the open circuit voltage, VC of t equal to 0 minus the open circuit voltage of cat, comma, VC of t equal to 0 minus, is not connected to the circuit. It's not connected. Look, there's an open circuit right here because of the switch being open. Right here. The switch is open, so there's no way that this open circuit voltage of the capacitor is connected to the circuit. So therefore, VC of t equal to 0 minus is equal to 0 volts because the open circuit voltage is not interacting with the circuit. Next question. What is voltage of cap after switch is or has been closed for a long time? In other words, this is asking what is VC of t approaching infinity? That's what it's asking. So let's solve for that. Steps. We're solving for VC of t approaching infinity in units of volts. We need to redraw our circuit in t approaching infinity and DC steady state. So let's go back, look at our circuit. That means the switch is now closed because t is at infinity. So the switch is closed, capacitor becomes an open circuit, everything else stays the same. Switch is closed, we have the resistor, current source. Now we have plus minus VC of t approaching infinity, R1, R2, R3. And how do we go about this? Let's look at our work. So the open circuit, what we need to notice is the following. Voltage across R1 is equal to, voltage across R1 as t approaches infinity is equal to the voltage of the capacitor as t approaches infinity, because R1 is in parallel to open circuit of the capacitor, cat. Okay, so let's redraw that. We now have this is IS of t approaching infinity. This is R3, 2, 1, plus minus VC of t approaching infinity. And now what do we notice? Notice R2 is in parallel to R3. So simplify even further. So now what we notice is that the voltage across R1 is equal to the voltage across the capacitor as time approaches infinity, which is equal to, using Ohm's law, R1 times who? Well, the current's going this way. So it's R1 times IS as t approaches infinity. Right? And that is going to be equal to what? Well, that's going to be equal to, what were the values again? 1 kilo ohm times 1 milliamp. 1 volt is equal to the voltage of the capacitor as time approaches infinity. Good job. Recap. We are looking for the voltage of the capacitor as time approaches infinity. If you look at the original circuit, we're just going to close the latch now, the switch. We're going to replace the capacitor with the open circuit voltage, an open circuit, because it's in DC steady state. And now we're just solving for the voltage across the capacitor, the open circuit capacitor, which we notice that VR1, the voltage across R1, is the voltage across the open circuit voltage, because they're parallel to each other. And then we didn't need to simplify the circuit, but by simplifying it, I hope it makes it clear that IS of t, IS, the current IS as t approaches infinity, that's going clockwise. It's going through R1, so you can use Ohm's law, shown here, to find the voltage across the capacitor as time approaches infinity. Next question. Question number 3. Pretty sure it's what's tau. Yeah. What is the time constant of circuit in seconds? So basically that's asking in the mathematic terms, what is tau c? Okay. Steps. 1. We're solving for tau of c in units of seconds. How do we do that? We need to redraw our circuit and time approaching infinity and DC, no, we just need to draw it for time approaching infinity. We need to remove the capacitor. We need to zero out all sources. And we need to calculate R Thevenin, which is equal to the R equivalent of the circuit between nodes what? A and B after removing capacitor. So let's redraw our circuit. We start off with the capacitor, the resistor, current source. But then we remove the capacitor. Whoops. We remove the capacitor, call this A, call this B, minus, plus. We zero out our current source, which means we're going to remove it completely because it becomes an open circuit. And this is what we are left with. This is what we are left with in step 2. So this is R1, this is R3, this is R2. Now, how do we find... Okay, so let's draw this another way. I want to keep A at the top. I'm just bringing my R1 here. So let me draw it and then I'll make some comments. If you can, we're just taking this whole circuit and actually, let's just do it this way. We're taking this circuit and imagine we're just shifting it 90 degrees counterclockwise. So, can I do that in this video? Imagine we're taking it and, can I rotate it? No. Imagine I'm taking it and I'm just rotating it to the left, counterclockwise by 90 degrees. That's what I'm trying to do here. Okay? You're going to have a circuit shown on the right-hand side. This is R1, this is R3, this is R2. Notice that there's a short here, a wire. Therefore, R3 and R2 are not going to be seen in the circuit because current will only go down here. It's going to ignore R3 and R2. So we are left with just R1. Why are we doing this again? Because now we found out R Thevenin is equal to R1, and in our third step, tau C is equal to R Thevenin times C, which means tau C is equal to 1 kilo ohm times how many farads? 10 microfarads. So tau C is equal to 0.01 seconds. Okay. Last but not least, question number 4. What is VC at t equal to 2 milliseconds? We can do that. What is VC of t at 2 milliseconds in units of volts? We need nothing other than VC of t equal to 2 milliseconds is equal to VC of t approaching infinity plus square brackets VC of t at 0 minus VC of t approaching infinity, close bracket, e to the negative t over tau c. Did I use negative t over tau c in the previous problem? Yes, okay. So that's all we need to do. Tau c. How do we do this? Well, we know that VC of t approaching infinity, we got that to be, what did we get that to be? 1 volt. We got VC of t equal to 0 minus. We got that to be 0 volts. And we got tau c to be equal to 0.01 seconds. Using these three numbers into this equation and using t equal to 2 milliseconds, you will get that VC of t equal to 2 milliseconds is none other than between 0.18 and 0.185, depending on people and their significant digits. Units of volts. There you go. So, coming back to everything that we did, we were given this problem. We found VC of t approaching infinity, VC of t equal to 0 minus, We also found tau C by finding R Thevenin times C. And using these three numbers, we were able to solve for V of C, t equal to, I think it was also 2 milliseconds. Yeah, it was also, 2 microseconds. Oh, no, milliseconds for this one. Sorry. Yeah, that's what we did. And then for the previous problem, we were given this circuit here, and we were able to calculate V of C t approaching infinity, V of C t equal to 0 minus, tau C, which is equal to R Thevenin times C, and we were able to solve for Vc of t equal to 2 microseconds. Thank you for joining. That's all you need to know about first order RC circuits, switch circuits.